Hello and welcome to a new root commit video. This time, let's see how to test a recent mainline Linux kernel on the Raspberry Pi 5 board. That will be pure vanilla, as people say, without any additional ingredients. I mean, no additional patch. You will see that's super easy to do with the Yocto project. But before we start, if you are interested in Yocto in general, don't hesitate to check out my Yocto Project and OpenEmbedded training course. There is a bit of theory, of course, but at least 75% of the time is learning by doing. Alright, so let's get started. The first thing to do is to install the required Ubuntu packages if you're taking the example of Ubuntu. Well, in my case, I already had them, but that's the first thing you need to do. So the first thing we do is create a repository for our work, like Raspberry Pi 5. And then the first thing to do is clone Pocky. That's the reference distribution from the Yocto project. So to do it, we go to git.yoctoproject.org, and Pocky is the first repository. Nice. And what we want to use is the styhead release, the styhead branch, because it corresponds to the latest stable release at this time. So just go and get it. So I take the styhead branch, as I told you. There we are, and the cloning is going on. The next thing I need is the Raspberry Pi, Meta Raspberry Pi layer that adds all the definitions it needs to build an image, a suitable image for the Raspberry Pis. So when I need to fetch a layer, I go to layers.openembedded.org. Super convenient website. Look for Raspberry Pi, there we are, that's the layer. And I go to the web repository to find its URL and clone it. This time I'm going to clone just the master branch because it supports both the styhead release and master as well. There we are. Okay, so now we're all set. We go inside Pocky. We source the init environment script. That creates a build directory. We're already inside it. And then we need to add our layer to the layers. As you can see, here are just the default layers. We need to add our own, right? Layers, add layer, and the path to the layer we fetched. And if you check again, right, now Meta Raspberry Pi is in there. All right. The last thing to do is just add a configuration that will specify the machine we want. If you look, there's a default machine somewhere. Which is this one, but we want another one, of course, corresponding to the Raspberry Pi 5. So here, when you want to look for a machine, what you can do is just check machines in the layer, and you will see all the machines, the machine strings that are defined. You can even see how it's defined. So the name we are looking for is Raspberry Pi 5. So Raspberry Pi 5, there it is. And then we're all set, so we can generate an image. Core image minimal. Of course, that will be the standard image for Raspberry Pi 5, as supported by the Meta Raspberry Pi layer. It's too early, of course, to have a mainline kernel, but at least we want to have something that works to begin with. So it's scanning the recipes, takes a bit of time. And now it's gonna run pretty fast because I already ran this before. And you know, BitBake is great at running the things it has run before very fast. So here it's running set scene tasks. It's fetching the output of tasks from the shared state cache. It's gonna be pretty fast. Of course, in your case, it will take a little more time at least the first time you run this. But the next times will be much faster. You'll be impressed. There we are. We have our image. And we didn't use the magic of video editing, as one of my friends says. Now let's prepare the hardware. Here's the Raspberry Pi 5, of course. A powerful USB-C power supply. I've got the official one, as you can see. You need a micro SD card to boot on. And last but not least, the Raspberry Pi debug probe. Its first usage is to make it easy to connect a serial line because you can't get it wrong. However, the main reason for using it here is that it's the port enabled by default at the bootloader and Linux levels. So if you want to use the serial ports on the GPIO pins, that's possible, but you'll have more things to tweak and more things that could go wrong. All right, so let's connect the debug probe to the board to see what's going on. So that's actually easy, but the thing is I like to keep the board in its protective case like that. And the protective case has its own cover with a fan, so it's actually easier to connect the fan first, like that. There we are. And then I can put the board in the case and then make the cable of the probe go through one of the holes in the cover and connect it. There we are. All right, we are all set. Everything is nice and well protected. Of course, you need to connect the other end of the probe to your PC. I will do that in the next step. And now I'm going to take the micro SD card and flash it with the image that we've just produced with Yocto. So that's the next step. So I actually inserted my SD card in my computer in a card reader. So let's see which one this is. Well, in my case, it says DB, I assume. Wait, so there was something flashed before. So let NSDB1, so two partitions, boot and root. So let's unmount them before we flash. So you can actually unmount by device file name, like B1 and B2. There we are. And now we can flash. I love to use BMap tool. That's actually a project that's now supported by the Yocto project, and it's a very efficient way to flash compared to DD, which doesn't account for the empty spaces between the partitions. So let's go copy, so that the path to the image, temp deploy, machine name, images, machine name, and then image name, machine name again, and it's the wick bzip2 file. Oh, of course, I forgot the destination, /dev/sdb. So you see how fast it was. That's amazing. Okay, now you see that the debug probe is connected because the light is on. Let me insert the SD card. There we are. And before we power up the board, what we should do is connect the serial probe on the PC side now. So I'm going to use TIO, it's a terminal emulator like Picocom, TTY-ACM0. Okay, so we're ready to receive the messages once the board boots. So last thing is to power up the board. Let's go ahead and do it. Ooh, it boots, good. So that's the bootloader, the Raspberry Pi bootloader. And now we are in the Linux kernel that boots. Right, I haven't connected the network, but it will give up. And then I log in as root and no password. And there we are. It's a Yocto generated root file system, as you can see. And let's check the kernel version now. Hey, 6.6, not so bad, but I think we can do better. So that's exactly what we are going to do. All right, so how to get BitBake to build a mainline kernel instead of the Meta Raspberry Pi one? We can hope to do it as the Raspberry Pi 5 board is supported since Linux 6.12, at least for the basic components. A first idea would be to hack the Meta Raspberry Pi layer and modify its recipes to build the Linux 6.13 kernel instead. After all, that's possible with open sources. Wait! Before I lose my most experienced viewers, don't do that! Never modify a layer released by somebody else. Never! That's a first-degree violation of the Yocto and OpenEmbedded Code of Conduct. Instead, you must take advantage of BitBake's overriding capabilities by adding a custom layer on top, which will override some of the things the underlying layers do. You'll see, that's very easy to do. So, let's create our layer, as I told you. So that's easy with the BitBake tooling. So BitBake layers, create layer, and the path to the layer. So at the same place as Pocky. So let's call it Meta mainline. Right, super easy to do, right? Let's have a quick look at what it looks like. Well, there's just a template layer with the layout conf file that you need to create and an example recipe. Very easy to do, so it's ready to share. And now we want to add it to bblayers.conf, so bitbake layers, add layer, and the path to the layer once again. All right, and then we can have a look at conf bblayers.conf, and our new layer is there, as you can see. All right, so let's look for the recipe we are trying to modify. So I'm going to use bitbake-s to list all the recipes being considered by BitBake in this context, like with the machine we've defined. Let's look for Linux in particular. There we are, and the only possible one is Linux Raspberry Pi with version 6.6, which confirms what we've seen before. I also want to confirm it's coming from Meta Raspberry Pi, so I'm going to use bitbake layers show recipes and a pattern. And this command allows me to see all the recipes that start with Linux dash. So this allows to find Linux Raspberry Pi that is indeed found from Meta Raspberry Pi. That's good. That's consistent. And you can also see there's the Linux Yocto recipe coming from the core layers, but those ones are skipped because well, the Meta Raspberry Pi overrode this and set its own recipe instead. For the same reasons, for similar reasons, Linux Dummy, it's also available. It's a recipe you can use in case you have provided the kernel, you're providing the kernel as a binary without building it with Yocto. In this case, it's disabled too, it's skipped too. The last thing I want to check too is where the kernel recipe is found in the layer. So let's run a find command, Meta Raspberry Pi -name Linux rasp star. Right, and indeed it's underneath recipes kernel /Linux. So we're going to use the same path in the layer that overrides the standard layer. Now we can create our new recipe in the new layer. So let's do that. We will use the same directory structure as in the original layer. So let's do that. So mkdir-p recipes kernel, if you remember. And I propose to call the new recipe Linux mainline, to be quite explicit. There we are. Then let's create the recipe from templates we will modify. So let me show you the two files. The first one is version independent recipe code. So in every recipe you have a description, a license, the checksum for the license in case the license changes in the sources. Then we're going to use the kernel class, which allows to compile a regular kernel, right? That's enough. S is where the sources will get extracted from a Git repository. Here we specify an additional defconfig file that will be used to configure the kernel, and that's what the kernel class expects, and provides here this recipe as a provider for the virtual kernel virtual recipe, right? And then that's the version specific part, right? So here we include the common stuff. So the idea here is to have like multiple versions that share the same code, except for the version specific stuff, of course. So here the source URI will be using the stable kernel release, the kernel tree that contains like typically 6.13, 6.13.1, 6.13.2. So we have to change the branch here. And we will also have to specify a specific commit ID here to use and check out for the kernel to be built. That's right. Now I can show you how to find the branch that you want to use, as well as the commit ID. So, well typically you also have here the URL of the tree you want to use. Then you have all the branches here. So really here we want to use the latest kernels. So I'm going to use the Linux 6.13.y branch, like for all possible releases in this branch, right? And then you see the latest one is 6.13.2. But here in the Yocto recipe, what you have to do is pass the actual commit ID. That is this one. So let me copy it. So now we can fill up the version specific part of the recipe. So there we are. So as I told you, the branch is going to be Linux 6.13.y, and the source revision, the commit ID, is just pasted from the website. There we are. Now the last thing we need is this defconfig file, the configuration for the kernel. So let's get it and make it from the Linux kernel sources. So let's clone them. Oh, okay, it's done. Faster than I could finish my coffee. So let's check the version. Right, so that's the latest RC. So we're still in master here, so I want to check out. Let's show all the tags. Right. Now, well, the one we want, git checkout v6.13.2. And look at the makefile, that's where the version is. Yeah, it's 6.13.2. To create the configuration and compile the kernel, you first have to set the target architecture, and here we're not on x86, we are on ARM64. So export arch equal ARM64. We can specify a cross compiler or use LLVM to cross compile, that's even easier. Right, and then make defconfig will pick up the default configuration for the ARM64 boards. And it does support the Raspberry Pi 5 indeed, but it's overly complicated. So a good idea here is to simplify it. So let's have a look, make manual config. We'll simplify the configuration a little bit to make the job faster or to compile, right? So an easy thing to do is go to platform selection in the menu and remove all the SOCs we don't want. We're just interested in the Broadcom ones, right? So I just take out all of them. This will substantially cut down the kernel compile time, believe me. There we are. And another nice thing we can do is also remove support for all the GPUs or all the kinds that are enabled as well. So and we don't want graphics this time. So here I looked for DRM with slash. And now you have this one result here, as you can see. Yeah, that's DRM. So now I can just press 1 on my keyboard and it takes me there and then disable it. Right. And that's enough for today. I think that we've got a pretty decent configuration here that we can use. Right. And the last thing to do is run make save def config. Because the configuration file we have here, the .config file, is full of default settings and it's not relevant to save them. So here it's better just to save the non-default settings, and that's the def config file that we get. Right, so these are all non-default settings. Right, and now the last thing to do is copy the def config file to our layer. So as the def config file is going to be version specific, Linux version specific, let's put it in a version specific directory. So I'm going to create one. So in BitBake, it's recipe name, and this time dash, not underscore, version. Right. And to make this even more useful, I can create a directory per machine. So imagine this recipe is being used by different machines to get the latest kernel mainline kernel. We can do that. So the def config will be machine specific. So when BitBake looks for the def config file, it will look through specific overrides that include the current recipe version and the machine name, and not the other machine names that we are not using currently. So the machine name here is Raspberry Pi 5. And then we can copy our stuff. So it's going to be Yocto, Raspberry Pi Linux, def config, right here. And we should be good to go now. By the way, let me show you what the recipe looks like now, the layer actually. Right, so you see in recipes kernel, we have the Linux mainline recipe. So that's the version specific BB file, the includes that could be common to multiple versions. And then we have per version and per machine specific def config files. Right. Oh, and I was about to forget, the last thing we need to do is set the kernel provider. So to replace like Linux Raspberry Pi by our new recipe. So let's do it. It happens in local.conf. So it's called preferred provider virtual kernel equal our recipe Linux mainline. And now we can check that our recipe is selected. BitBake-s Linux. There we are, Linux mainline. Good. And then we can build our image again with the new kernel. Here we are. Oh, the coffee is cold. The build stopped with an error. All right. We can investigate it, fortunately, no problem. So investigating this error here, it's failing to find overlays, overlay map.dtb. So let's have a look at Meta Raspberry Pi and see what the Meta Raspberry Pi is trying to do. Here we're still using Meta Raspberry Pi to build the bootloader and the way you boot the kernel. So that's still something very specific to the Raspberry Pi. We want to keep that, of course. So let's have a look at Meta Raspberry Pi and look for this file it's looking for. Okay, and eventually we find that there's a list of overlays that are added here in the RPI base recipe, right? So here we don't want to manage overlays for add-on boards like hats. We just want to support the base board with the standard Linux kernel. So let's actually set this variable to nothing. And I've already done this here. So you see, I set it empty, and that will override the defaults. So yeah, in a nutshell, we still want to use the default mechanisms for building the way the Raspberry Pi boots. And at last, we can try to build the image again. Bitbake core image minimal. There we are. Oh, there we are. It's over. Then we have our image. Hey, so let's copy it to the SD card and try to boot it. So we run the map tool again. Right, done. All right, so the moment of truth. Let's boot the board again. Suspense, suspense. It boots, but which version? Ooh, that's the right one. Great. Well, that's it, my penguin friends. I hope you liked this video and it makes you feel like trying the mainline kernel on your Raspberry Pi board or other boards. You could test the full preemptible kernel option that was added to 6.12, for example, to check the real-time capabilities of your system. You can also check the presentation I made at the OpenEmbedded Workshop in Brussels this year, showing how to do the same with QEMU with BeagleBone Black and BeaglePlay. The link is in the description below. This video was sponsored by the RM-R Universal Cleaner. This incredible product erases all your programming mistakes and more. Unforgettable experience guaranteed. That's really over now. So if you are interested in supporting Root Commit for creating more videos of this kind, you have plenty of options. You can register to one of my courses or ask your employer to order one at your location. You can like this video and subscribe to this channel. And you can also buy a Root Commit t-shirt or buy me a coffee. Thanks for watching and see you very soon for more videos.